All right, here comes the massive jumbo question. If you could do this one, you'll nail this test. I mean, this has got all kinds of stuff on here that you would need to be able to do. So this is a very, very good question. Lots of stuff going on here. So the question is, what solve for S and R? So we have unknown values here in this set of data, but you're going to have to know the rate law of this data to be able to predict the rate when you know the concentrations, or predict a concentration when you know the rate and some other factors here, other concentrations. So we got to figure out the rate law. That's the first thing we got to do here. It's a big question. So what I want to do is figure out which experiments should I use to determine the order, because remember, rate equals K, and that would be times A to some power times B, whatever order it is, to its order, times C to C's order. We have to figure out, so we have to figure out what these orders are right now. So let's do that right now. So for concentration A, I need to find an example where A is changing, but B and C are not. And I wouldn't even consider thinking about I wouldn't consider looking at 5 and 6, because you can't make a conclusion here, because this is incomplete data. This is kind of, we got to figure something out here. So let's just look at these four. So for A, I would like to look at well, let's see, maybe 1 and 4. 1 and 4, we can see A is changing, but in 1 and 4, B is staying the same and C is staying the same. So the change in rate is entirely because of the change in A. So for A, concentration A, I'm going to use experiments 1 and 4, and 1 is larger, so I'm going to put 1 over 4. So 1 and 4. And what happened here between 1 and 4? What happens is 385 divided by 192.5. The concentration doubled. The concentration doubled between 1 and 4. So this is doubling to go up to here. So the concentration doubled. It's going to be raised to some power. And what happened to the rate? So between these two. So I'm going to say 6.75 divided by 3.375, and the rate doubled. Well, that's nice. Therefore, that's first order. So A is a first order reactant. Let's do the same thing for B. So which ones will we look for B? We need to see things, examples where B is changing but C and D are not. And I'm going to look at maybe 2 and 3. Between 2 and 3 we see B is changing, but A is staying the same, and so is C. So this rate change is entirely because of the change between 2 and 3. So I'm going to say 2 and 3 for B. In this situation between 2 and 3, I would say that we have 370 divided by 185. That's a change. It's 2. So that concentration doubled also, but that's to the y power. And what happened to the rate of this reaction? That would be 13.5 divided by 6.75, and that also doubled. Very nice and easy. Very convenient. That means that B is also first order. B is also first order. Let's try C. For C, let's see an example where C is changing, but C is changing, but A and B are not changing. So let's take a look at this real quick. This is changing. Maybe 3 and 4. A is staying the same, B is staying the same, but C changed. So I'm going to say 3 and 4. And what happened between 3 and 4? Well, the change is 195 went to 390, so I'd say 390 divided by 195. I always just pick the larger divided by the small to get this, and that also doubled. So by doing this little division here, Some of these things, it doesn't look like it doubles right off the bat, but if you do use your calculator and just divide small by large, you can kind of see what happens here. So that doubles, and what happened to our rate? So that would be 6.75 divided by 3.33. So, oops, I put too many threes there. 6.75 divided by 3.375. Bam. That's 2. How convenient. They're all first order. So our rate law would be this. The rate equals K times A times B times C. And they're all first order. So that's our rate law. But we should solve for K. We need to know what K is in our rate law. So K equals the rate over A, B, C. So let's just choose one of them. Let's just choose the first one here. So K equals the rate, which is 6.75, and this is in pressure this time. This is in pressure, millimeters of mercury. So this unit is the formation of D was formed in millimeters of mercury per second. Millimeters of mercury per second. Which one are we choosing here? Number 1. And we're going to have A, which is, so we're still using number 1, 385 millimeters of mercury times 185 millimeters of mercury times 195 millimeters of mercury. Millimeters of mercury cancels out with one of them, so we have seconds and 2 of those. So to solve this, 6.75 divided by 385 divided by 185 divided by 195, and I got a really small number, so I'm going to put this in scientific notation. So my answer for K is, it's a small number, 4.86 times 10 to the negative 7th. So I'm going to put that right here. K equals 4.86 times 10 to the negative 7th. And my units are per millimeter of mercury squared seconds. Now that's my rate law. This is an important piece of the puzzle because with this, we can then solve our 5th one, S. So to solve for S, I'm just going to use my rate law. I'm solving for S, so the rate, which is S, is equal to K, which is this number here, 4.86 times 10 to the negative 7th over millimeters of mercury. I'm going to put it twice, millimeters of mercury, because that's squared, times seconds. A, so 550 millimeters of mercury. B, 250 millimeters of mercury. And C, 125 millimeters of mercury. Millimeter of mercury cancels out with millimeter of mercury, millimeter of mercury, millimeter of mercury. Our answer is millimeters of mercury per second, which is rate, so that's a good thing. So let's just multiply this through. Let's try to kind of fit this on here. Where can we do this so you guys can see it? Put that up there. So let's do that. 86 raised to 10 to the negative 7th times 550 times 250 times 125. So I got 8.35. S equals 8.35 millimeters of mercury, that's right here, per second. Now let's just take a look. Does that make sense? These concentrations in 5 are similar to, 500. There's almost 400 here. There's 250. There's a 370, 180s, 125. So they're similar to these ones. So is our number 8.35 fit in this? Yeah, it fits in real nice. So that makes sense. If it was a really huge number or a really small number, I didn't show that there very well. So 8.35 would be our answer here. And that kind of fits in this trend. It doesn't look like it's out of place. So odds are, looks like we did it right here. Let's try to solve for R here. So I'm going to need, again, my rate law to do this one. I'm going to solve for R here. So the rate law that we already determined is rate equals, I'm just rewriting it here, K times A times B times C. I just pulled that from here. And I'm going to also say K equals, from here, 4.86 times 10 to the negative 7th millimeters of mercury squared seconds. Okay. Okay. Now we're going to solve for A, basically. We're going to solve for A, because that's where R is. So to solve for A, let's rearrange, and that would basically leave A there, and then all of this would come down, cross multiply. So that means I could take this and these and cross multiply, bring it down here. So I can say rate equals, rate over K times B times C equals A. So I leave the A here and I bring the K down here and I bring this, cross multiplying. So A, K down, bam, bam, bam. So now we can solve for A. So let's plug in these values on the sixth one and solve for A. So A is basically our R, our unknown. Our rate is 2.00 millimeters of mercury per second. So that's our rate. Let's put in K. K is 4.86 times 10 to the negative 7th millimeters of mercury per second. Oh, I'm sorry. Actually, I did that wrong. It's over millimeters per second. So that number, and then it'll be divided by that. So the denominator of a denominator is actually a numerator. So we can move these units here as a numerator. So that's millimeters of mercury times millimeters of mercury, because it's squared, times seconds. That's K. B is 350 millimeters of mercury. So 350 millimeters of mercury. And C is also 350 millimeters of mercury. 350 millimeters of mercury. Okay, I know it's kind of small. 350 millimeters of mercury. It's kind of small there. A little easier to see there. So canceling things out, millimeters of mercury cancels with this millimeters of mercury. This one cancels with this one. Seconds cancels with seconds. And our answer is in millimeters of mercury, which is excellent because we want the concentration. So units canceling out, this would tell me right now if I did something majorly wrong. I should be able to catch it right there. So if I make a mistake on this one, at least it's not in this setup. So now I've got all my numbers in place. We got to solve this thing. So let's do it. 2 divided by 4.86 times 10 to the negative 7th divided by 350 divided by 350, and I have the concentration of A is equal to 33.6 millimeters of mercury. Let's just take a look at that. Does that make a lot of sense here? So if this was 33.6, that's a lot smaller. 33.6 is a lot smaller than these ones. However, 350 is at the highest end of this, and 350, so these are much larger. If these are going to be larger, then that would have to be smaller because they're all constants because they're all first order. So I'm okay with it. You do the work, and hopefully we agree on it. Let me know what you think. So A is 33.6 millimeters of mercury, concentration A, or solving for unknown R. And let me know what you think. Good luck, guys.